Okay, so this is 6-1, referring to polygons. Hopefully you read through the test booklet definitions, which we can refer to later. But now let's look at the notations. Polygon. It can be any number of sides. Here we have an example which is 5-sided figure, so that would be the pentagon. And you can label it according to the letters, and you have to go in order around the polygon. A, B, C, D, E. That's the name of the polygon. The sides of the polygons are the two edges, or the edges connecting two vertices, AB, side BC, side CD, side DE, or side EA. But a vertex is not the same thing as an angle. A vertex is just the point where the two sides connect. That's vertex A, vertex B, vertex C, vertex D, and vertex E. You also have angles. They're just not here on this page. Angle A, B, C, angle D, C, angle D, angle E. All right, a diagonal is a segment connecting two non-consecutive vertices. Two vertices that are not side by side. So this vertex connects to this vertex, and you have a diagonal. This vertex doesn't connect here. That's the side of it. But if you go to the next vertex, that creates a diagonal right there, etc. Turn to page 382 of your regular book, and you're going to see a list of all the polygon names dependent upon the number of sides that they have. So go ahead and copy those in. If you turn the page in your notes, you'll see this chart here. Go ahead and fill in all those names so that you have those to refer to. Go ahead and hit pause, do that, and then come back. So, tell whether each figure is a polygon. If it is a polygon, name it by the number of its sides. We had these definitions of polygons earlier, that a polygon has to be a closed figure, meaning that there's no open gaps. It has to have all sides that are segments, no curves, and it has to have no crisscrossing, no overlapping of the sides. So for this first one here, determine if it's a polygon, and to me, it looks like a polygon. There's no open gaps, they're all segments, and no curves, and nothing is overlapping. So this is a polygon. However, name it by the number of sides. Look back at this chart here and figure out what the name would be according to the right number of sides. Count the sides here. 1, 2, 3, 4, 5, 6, 7, 8, 9 sides that I see. So if you look down your chart, you should see that that is a non-agon. Non-agon has 9 sides. Number 2, this is not a polygon. The problem is that you have a curve there. And with curves, it's not a polygon. Number 3, what do you think? Answer is no, because it has an open gap right here. It's not connected, and also you have overlapping sides right there. They crisscross, so that makes it not a polygon either. For a polygon to be regular, it must be both equal angular and equilateral. All the angles must be the same, and it must be equilateral. All the sides must be the same. Name the only type of polygon that must be regular if it is equiangular. Think about that for a second. We had one already. What kind of shape was it that if we knew it was equilateral, then it automatically had to be equiangular? It was the triangle. Okay, if a triangle is equilateral, we automatically know it's going to be 60, 60, 60 for the angles. But think about this. A quadrilateral doesn't work that way. An equilateral quadrilateral, like a rhombus, is not necessarily equiangular. A rhombus doesn't have to have all matching angles. It just has to have matching sides. A rhombus could look like this. Okay, and vice versa, it works as well. If an quadrilateral is equiangular, all right angles, 90, 90, 90, 90, it doesn't have to be equilateral. You can have a rectangle that has all right angles, but yet it's not equilateral at all. Two sides are longer than the other two. Even though it has 4 right angles, it does not have to be equilateral. Okay, so definition of a regular polygon. Regular in this case does not mean ordinary. It means 2 specific things. A regular polygon has to be equilateral and equiangular. So when you look at this case up here, it has to be equilateral. All these edges, in this case it's a hexagon, so all 6 sides must be marked equal to each other. And there's certain rules that are only going to apply when you have a regular polygon of any kind, so make sure that you find out that first so you can use your rules. But it also has to be equiangular. This angle has to be equal to all the other angles in the picture. And that's what makes it regular. When a definition says a regular polygon, then they mean it has to have this first before the definition could apply. Concave and convex. You've probably heard about this in science. Let's apply it to shapes here. Concave has that base word cave in it. And I always think of things that are concave as things that cave in. Okay, there's pieces of it that would cave in. So looking at the shape right here, this piece is caving inward. This piece is caving inward. So that makes it a concave shape. Here, there's no pieces that are pointing inwards or caving inwards. Everything is caving, or I'm sorry, is pointing outwards. So there's no concave here. That makes it convex. So the definition is that the pieces, there is at least one piece that caves or points inward. That's what makes it concave. There's another official definition about crossing over a diagonal, but this one makes sense. And convex is anything that's not concave. Any shape, any polygon where there's nothing pointing inwards, everything's pointing outwards. Tell whether each polygon is regular or irregular, then tell whether it is concave or convex. So we have 2 things to look at. Number 5, is it regular? Well, these 4 sides all seem to match, but this 5th side doesn't have any markings on it. It's not congruent to the other ones. So therefore, it is not regular. It's irregular. And then we have to decide if it's concave or convex. Well, I definitely see a piece here that's caving in the middle. That means that it has to be a concave polygon. This one, is it regular or irregular? Every side has matching marks and every angle has matching marks. That makes it a regular polygon. Is it concave or convex? Can you find any pieces caving inwards, pointing towards the inside? No, so that makes it convex. And lastly, number 7, is it regular? No. These sides all match, but these 2 sides have something different. This angle is also different from the rest of the angles, so that makes it irregular. And I don't see any places pointing in or trying to cave in there, so that makes it a convex polygon. Next one. Okay, so here's proof that the exterior angles, the outside angles, will always come to be 360 when you add them together. Here is 1, 2, 3, 4, 5. Here's a pentagon, and it could work for any shape if you did the same thing. Every corner has the potential for an exterior angle extending out just like we did with triangles. Well, there's going to be 5 exterior angles. So watch. If I take this one outside angle here and I move it over to the side, and I take this exterior angle and I move it over to the side, and I do that with all my exterior angles and I combine them together over here, and this one, you move it over there, and this one, the last one, you move it over there, what do you see happening there? Think about it. It started right here, and it came all the way back around. How many degrees is that? When it comes all the way back around, that's 360 degrees. A full circle is 360 degrees. Okay, so that can happen, and you could do this exact same thing for any other polygon, and it would work the same way. So now let's make sure we have it written in our notes. Okay, it's really important to know what you're dealing with here. It's an interior angle sum theorem. The sum of the interior angles of a polygon with n sides. The n is your determining factor. If there was 3 sides, it would be a triangle. If there were 8 sides, it would be an octagon. If there were 10 sides, it would be a decagon. This one here is 1, 2, 3, 4, 5. This one's a pentagon. N equals 5. So the formula that you need to know and write down in there is n minus 2 times 180. N just represents the number of sides. So in our example, n is 5. So I'm going to go over there and I'm going to say that it's 5 minus 2, that makes 3. And then you always have to go back and multiply it by 180. Okay, so that's 3 times 180, and you get 540. Okay, you can memorize that a pentagon is going to have 540 degrees for the measure of its interior angles. Or you can look in your chart or in your test booklet if you have it there. Okay, the exterior angle sum theorem, we just talked about that. We just looked at a proof of that. The sum of the exterior, this one's all about the exterior angles. Okay, the sum, the total exterior angle sum is always going to be 360. It does not matter how many sides there are. There's no n here determining how many sides there are. It's just always going to be 360, always, no matter what the shape is, no matter how many sides there are, it's going to be 360. These examples we'll do in class. These examples we'll do in class. Okay, we'll do this one in class too. But turn the page till you find this chart again where you have already written down all the names of the polygons. Let's look at these other characteristics here. The sum of the interior angles for regular polygons is n minus 2 times 180. That's the total. But if you wanted to find each individual angle, you would take that total and you divide by n, the number of sides. For the sum of the exterior angles of any kind of polygon, it's always 360. But if you want to find each individual exterior angle on the outside, you just take that total 360 and you divide by the number of sides you have. You can do triangle and quadrilateral. I'm going to do the pentagon with you just so you can see how the formulas work. Pentagon has 5 sides, so plug in the 5 right there. 5 minus 2 equals 180. That becomes 3. 5 minus 2 is 3 times 180. You get 540 degrees for the inside angles of any pentagon. The next column wants you to find each angle inside the pentagon, and this only works for when they're equilateral and equiangular. So I don't have to do the top part again. I already know it's 540, but I have to take that 540 and I have to divide it by 5 sides or 5 angles, and you get 108. The sum of the exterior angles, I don't even care how many sides there are, it's always going to be 360. But to find each individual angle, you have to be able to take it and divide the total 360 by 5 sides, and you get 72 degrees for that one. You finish the rest of the chart by tomorrow. Okay, just plugging in the numbers and try to understand the difference between each of those columns, which we will discuss tomorrow. Don't forget, when you're done, go back and answer the questions for 6-1 online.